Chapter 20 is all about amines. Before we get into the chemistry of amines, we're going to briefly review the nomenclature of amines. So primary amines can be named in two different ways. The names in black are common names, and that's going to follow the pattern of alkyl amine. So our first compound says methylamine. That's your alkyl group, followed by the suffix amine. The IUPAC way of naming is going to be to say the alkane name and then add the suffix amine. So methanamine versus methylamine. The third compound says isobutylamine. Isobutyl is a common alkyl group. The IUPAC way of naming it would be to find the longest chain, which is 1, 2, 3 carbons, and then indicate the substituent coming off of the longest chain. So 2-methyl-1-propanamine. Secondary amines can also be named in two different ways. You will find your longest carbon chain for IUPAC naming, and that will be the family name that you use, so ethanamine. And then you would indicate that the nitrogen has an additional substituent on it by saying N-methyl. The common way of naming secondary amines would be to just list off the two different substituents coming off of the nitrogen and put them in alphabetical order. So we have an ethyl group and a methyl group. E comes before M. And when you have two of the same alkyl group, the common way of naming would be to put a di in front of it, so diethylamine. The IUPAC way of naming would still be to use the longest chain, ethanamine, and then indicate the substituent as N-ethyl. Tertiary amines are going to follow the exact same type of nomenclature. So again, find your longest chain, and then everything else is a substituent coming off of the nitrogen. And if those substituents are different, you list them out differently, just like you would having substituents on different carbons of an alkane. Aryl amines, we tend to stick with the more common naming. So you learned the name aniline instead of using benzene amine, and then we tend to indicate substituents off of aniline. When the amine group is a substituent, its substituent name is amino. So this will happen when you have other functional groups that are of higher priority. So an alcohol or a carboxylic acid is going to have a higher priority in naming. So let's do a little practice. Go ahead and pause for a second so that you can try and come up with your own names and your own structures. So for the first compound, this is aniline. And then we have a methyl substituent coming off of the nitrogen. So this would be N-methyl aniline. It's important to put the N there. If you did not put an N on there, the methyl group would have to be coming off of the ring somewhere. So the N is very important to indicate. Now the second compound, you have to recognize that the alcohol is actually the higher priority. So this molecule is going to be a derivative of propanol because this is the 3-carbon alcohol. So this would be 3-amino-propanol. And you should also indicate that the alcohol is coming off of the first carbon. For our next two, you're given a name and you have to come up with a structure. So I would start building up from the biggest piece. So this is a bunch of substituents coming off of aniline. So the first thing I would do is draw aniline. And then it says N-ethyl, N-methyl. So that's my structure. The next one says p-aminobenzoic acid. So benzoic acid is the bulk of my structure. And then I have an amino group in the para position. So p-aminobenzoic acid. You can also call it 4-aminobenzoic acid. Okay, so we also need to think about the structure of amines before we go into their chemistry. It's important to know their geometry and especially the electron pair geometry before you move on. So the molecular geometry of an amine is trigonal pyramidal. The electron pair geometry is tetrahedral. So you have your amine. Notice that the R groups coming off of the amine are not in the same plane. That's what gives it the molecular geometry trigonal pyramidal. And the electron pair geometry is tetrahedral because when you include the fourth thing of the lone pair on the nitrogen, this is actually a tetrahedral structure. Also remember that nitrogen is more electronegative than carbons and hydrogen. So if you were to have trimethylamine, you would have more electron density on the nitrogen and less on the carbons because of the dipole. Also because of this tetrahedral shape, if you were to have different carbon groups on nitrogen, so R prime, R double prime, R triple prime, technically there are two different enantiomers of these compounds that can be interconverted through a pyramidal inversion. But realistically, this is happening so fast that you're never going to resolve one enantiomer versus the other. So they're considered to essentially be the same molecule. However, if you have a quaternary ammonium salt, you're not going to have that inversion anymore because you no longer have the lone pair. And so you can actually have enantiomers of the ammonium salts. So the main way that we've seen amines used in organic chemistry so far is as weak bases. They are stronger than water, but weaker than hydroxide or alkoxides. And the way that you can determine the strength of an amine as far as its basicity goes is to compare the pK values of conjugate acids. So for example, all of these are protonated amines, and the more acidic the conjugate acid is, the weaker the base. So ammonium is the conjugate acid of ammonia. So ammonia having the most acidic conjugate acid is going to be the weakest base versus ethylamine on the far end here. So this is how you can compare the basicity of different amines. The reason that the ethylamine is actually a stronger base is that alkyl groups are electron donating. This is going to stabilize the positive charge that is formed when the conjugate acid is made. And the more stable that positive charge is, the least likely it is to want to give back that proton. So that means that this is a weaker acid, and also that ethylamine must be a stronger base because it's good at picking up a proton and keeping it. In this example here, you see an amine that has one alkyl group on it that alkyl group is donating electron density to the nitrogen's lone pair, and so it's able to pick up a hydrogen from water and create an ammonium hydroxide salt. Aromatic amines are weaker bases than alkylamines. So for example, you have a cyclohexyl ammonium here, and its pKa is about 10.64, but then you look at the conjugate acid of aniline, and it's 4.58 for the anilinium ion. So the better acid is going to have the weaker conjugate base. So aromatic amines are weaker. Also notice that, again, putting on substituents onto the benzene ring, these are electron donating, so alkyl substituents. That's going to make this a weaker acid, which means that its conjugate base is a stronger base. So the reason why is that phenyl groups are electron withdrawing, and you can actually see that when you look at the resonance form. There are so many places where you can delocalize the lone pair from the amine onto the benzene ring. So even though this involves separation of charge, you can still see that the ortho and para carbons are able to have the lone pair and a negative charge on them through resonance. Now, amides are not going to be as basic as amines. Notice that the carbonyl group is pulling electron density away from the nitrogen, so that's going to make it a much less effective base. It's actually even less basic than aryl amines. The pK of the conjugate acid of an amide is pretty close to 0, which is actually a very, a strong acid, stronger than most of your carboxylic acids. So I forgot to indicate this already, but any slide that has an asterisk on it means that this is essentially repeat information. So this is stuff that you are already responsible for because you've already learned it. Hopefully acid-base reactions involving amines sound really familiar to you. So an amine can be reacted with an acid to create an aminium salt. So the nitrogen lone pair can pick up the hydrogen, give the electrons back to chlorine, and that's going to give you an aminium ion with the chloride as the counter ion. You can do the same thing with a secondary amine. You can pick up a hydrogen, give the electrons to bromine, and I have an aminium bromide salt. And you can also do this with a tertiary amine. However, you cannot protonate a quaternary ammonium ion. So in this case, this is one that already has 4 alkyl groups on it. There is no lone pair left on this nitrogen, so it cannot pick up a proton. This is a pretty cool trick because amines tend to not be very water soluble, but if you can protonate it with an acid, you create a water soluble aminium salt.